Today I'd like to have a look at gauge blocks, and these are common to the machine shop. They're used as a standard to check other equipment against, such as calibrating a micrometer or doing a build-up to create an angle. And we'll have a look at that in a little while. This is a common set of 83 gauge blocks, and they come in different degrees of accuracy. A AAA set, which is a master set, a AA set, which is a laboratory set, an A set, which is an inspection set, and a B set, which is a working set. Commonly the B set will be found on the machine shop floor, and it typically will hold 83 blocks. In the box here there are two blocks that will be wear blocks. These wear blocks will be at the end of any build-up that you make, because the environment can be hostile, and if we're going to wear any of these blocks out, we want to wear out just two and have to replace those. We then have the fourth decimal place, which goes from 0.1001 to 0.1009. The second series will be the third decimal place, and these ones will go from 0.101 to 0.149. The third series will be the second decimal place. These ones will go from 0.150 up to 0.950. And then the fourth series will be the inch blocks. They will go from 1 inch up to 4 inches. And that will be the complete set of the 83 blocks. Inside the box of the gauge blocks, you should have a certificate which will show you the accuracy of the blocks. Let's have a look, for example, 0.1005 block. It has an accuracy of +1, and the deviation is micro inches, which is 0.00001 inches of deviation. Now you notice some of the blocks are larger than that, but this is a very, very small deviation, and the accuracy will be great. In the example we'll see in a couple of minutes, we're actually going to check the angle of a part that's been machined, and the angle is, for argument's sake, just for this test, is for 30 degrees, 50 minutes, 12 seconds. If we do the trig and we multiply it by 5, because the distance between the centers of a sine bar are 5 inches or multiples of 5, it works out to an answer of 2.5629 inches. We're now going to take this size and we're going to start to look for some gauge blocks for it. The first thing we need to do is we need to remove the wear blocks, which are 200 thou, 100 thou each on each end, so that'll total 200 thou. That gives us a total now of 2.3629. We want to have a look at the last decimal place, and we want to use the first series of gauge blocks in order to get rid of this decimal place. So if we use the 0.1009 gauge block, it will allow us to get rid of that last decimal place. Now you can see the answer is actually 3 decimal places. We want to take this and we want to get rid of the last decimal place, and we want to make the second one either a 5 if it is greater than 5 or a 0. So if we go in the second series of gauge blocks and we choose 0.112 and we subtract that, we end up with a total of 2 inches 0.150. And this has created it with a second decimal place is now 50 or 5. Okay, so if we go into the third set of gauge blocks and we choose a 0.150, it will now give us a remainder of 2 inches, and then we'll choose the last gauge block, which is 2 inches, and that will give us a remainder of 0. So the gauge blocks we're going to use are going to be 2 inches, 0.150 inches, 0.112 inches, 0.1009 inches, and 200 thou wear blocks, which are going to give us a total of 0.200 inches. Here are the gauge blocks we're going to use, and we have them laying on a surface plate. So what we've done is we've pulled out of the set the actual blocks we're going to use. So here is the one wear block, which is 100,000th of an inch. Here's the other wear block, which is the other 100,000th of an inch. The first series, the 0.1009. The second series, the 0.112 inches. The third series, which is the 0.150 inch. And then the fourth series, which is the full 2-inch block. These blocks are hardened, and they're ground and lapped, and they're very, very flat. What we're going to do is we're going to put these blocks together. Before we put these blocks together, we want to make sure that the faces that are going to mate within the next block are clean. So as you can see, it's a good idea to clean them on something such as the back of your hand. The reason we're choosing the back of the hand is because there's less grease and dirt in the back of the hand than there would be in the palm of the hand. You also could use a lint-free rag, which would be another alternative. Okay, now we're ready to start sliding these blocks together. And what we're going to do is we're going to pick them up, and the faces that we've cleaned we're going to slide in opposite directions. It's called ringing the blocks together. So the surfaces, again, where they're going to mate are very, very flat and ground. So as we slide them over each other, what it's going to do is it's going to create a seal with no air in it, and it will almost feel like they're magnetized together, even though they're not. And the reason for this is so that there's no error in measurement, because if we were to stack a whole bunch of blocks together and there was dirt or air in the middle, we would get an inaccurate reading once we had it all built up. Here are the gauge blocks rung together on the surface plate, and you can see the wear blocks on either end of the build-up, which will come into contact with other surfaces.
Micrometers are produced in various precisions, both in metric and English units. In every case, it is the thread pitch of the spindle screw that makes each type different. The thread pitch is the distance between two adjacent thread crests. In this example, the thread pitch of the micrometer spindle screw is precisely 1/2 millimeter. Each revolution of the thimble moves the micrometer spindle 1/2 millimeter. The micrometer has a reading line on the sleeve. The vertical graduations on the top of the reading line each represent a single millimeter. The vertical graduations below the reading line indicate 1/2 millimeters. The beveled edge of the thimble is graduated into 50 divisions. Since a single revolution of the thimble moves the spindle 1/2 millimeter, each thimble graduation equals 1/50th of 1/2 millimeter, or 1/100th of a millimeter. The thimble is rotated and the spindle advanced until the feature is held between the anvil and the spindle face. To read this micrometer, add the number of millimeters and 1/2 millimeters visible on the sleeve to the number of hundredths of a millimeter indicated by the thimble graduation, which coincides with the reading line on the micrometer sleeve.
Dial indicator is a very important comparator used in mechanical industrial measurement applications. In this video we'll learn about dial indicator. This video will cover the following. 1. Working principle of dial indicator. 2. Its construction. 3. Working. 4. Applications. 5. Advantages and disadvantages. If you are new to ADTW, click on the subscribe button below and turn on the notification to get all the updates. Let's start. Working principle of dial indicator. It operates on the principle that a very slight upward pressure on the spindle or plunger at the contact point is multiplied through a system of gears and levers, and it is indicated on the face of the dial by the pointer. Dial indicators consists of a body with a round graduated dial and a contact point which is connected with a gear train so that pointer on the dial face magnifies and indicates the amount of plunger movement. Construction of dial indicator. Dial gauge consists of following parts. Circular dial body. Pointer or indicating hand. Round graduated dial. Revolution counter. Bezel. Bezel clamp. Dust cap. Stem. Plunger, which is subdivided into spindle and contact point. In the side view we can see other parts: crystal, back, mounting lug. After opening the body of dial indicator we can see internal parts, and those are rack, rack guide, gear train, hairspring, and coil spring. Working of dial indicator. Before we see the working of dial indicator, let us first understand how the magnification is achieved with the help of gears. Consider two gears A and B. These gears are mashing with each other. The number of teeth on the gear A is less compared to gear B. The smaller gear A is called pinion. When we rotate pinion by one revolution, the gear B rotate through a small angle. This depends on the gear ratio. Now, suppose we rotated gear B by one full revolution, the number of revolution of pinion is more. With this basic understanding, now we can see how the magnification of the plunger is achieved in the dial gauge. To obtain the necessary high magnification ratio in this instrument, gear and pinion arrangement is used. By arranging the gear train in a manner similar to a clock movement, there is a plunger which is a perfect sliding fit in its own bearings. This carries a rack which accurately meshes with a pinion A. The rotation of the plunger about its own axis is prevented by a pin attached to it, which is located in a slot in a rack guide. In order to keep the plunger in an extended or normal position, a light coil spring is employed. A small movement of the contact point causes the rack to turn the pinion A with which it is meshed. A large gear B is attached to the same spindle as pinion A. The gear B is further meshed with a pinion C, which thus magnifies the movement of pinion A. Attached to the second pinion C is another gear D which meshes with a third pinion E, mounted on the same spindle as the indicator pointer. This magnification is further enlarged at the tip of pointer by an amount depending upon its length. In order to take up backlash, a light hair spring H is always fitted to the dial gauge gear trains by meshing a gear F to pinion E and attaching spring with gear F, also to prevent gear backlash. The gears are precision cut and the movement assembly resembles that of high-grade watch. After final assembly, each dial gauge is thoroughly tested and checked and properly calibrated by either a calibrated micrometer head or by the use of slip gauges. If the pointer moves more than one revolution, a revolution counter is also incorporated, which will correctly indicate the number of revolutions made by the main pointer and thus enable a complete reading to be made when the gauge is used for direct measurement. Also, we can rotate the round graduated scale to set the pointer to 0. In some dial indicators, 2 range pointers are given on the bezel, which are used to set the range. Applications of dial indicator. 1. Comparing 2 heights or distance between narrow limits. 2. To determine the errors in the geometrical form such as ovality, roundness, and taper. 3. For taking accurate measurements of deformation such as intention and compression. 4. To determine positional errors of surfaces such as parallelism, squareness and alignment. 5. To check the alignment of lathe centers by using a suitable accurate bar between the centers. 6. To check the trueness of milling machine arbors and to check the parallelism of shaper arm with table surface or vise. Advantages. 1. Dial indicator is the most flawless tool in taking linear measurements. 2. Moreover, dial indicators are also be used to measure several deviations by aligning with some other attachments. 3. Due to small tolerances, the size of the tool is very compact and thus, it can be used seamlessly in mass production. 4. Out of roundness, the amount of taper can also be measured efficiently by dial indicators. 5. The tool is very efficient to assure the quality of a workpiece. 6. Dial indicator is also useful in dimension control. Disadvantages of dial gauge. 1. The precision of dial indicators often lost due to the vibration of machinery. 2. Another crucial disadvantage of the tool is the parallax effect. 3. Space constraints can lead to installing the tool at an angle, due to which precision of measuring device is lost. Hope you have understood the dial indicator. If you want more in-depth videos like this, then subscribe this channel and click on the bell icon to get notified for every special video we upload. Also, if you have any doubt or opinion, comment it below. And help us by sharing this video with your friends.
The next part of our inspection is going to deal with measuring cylinder bore wear, cylinder bore out of round, and cylinder bore taper. Now, this could be accomplished with a telescoping or snap gauge and an outside micrometer, but by far the most accurate way to measure these things is to use a bore gauge. So this video is going to deal with setting up and using a bore gauge and how to actually take those measurements. We've got a bore gauge here and a 3 to 4 inch outside micrometer, which we're going to need for this measurement. Now, I've already calibrated the micrometer, so that's done for us. The bore gauge consists of a dial indicator, the bore gauge handle itself, and we have a variety of adapters Now you're going to have to select the adapter you need based on the size of the bore, and in our case we're going to use a 3" and 600 thou, and we're also going to have to adapt them just a little bit longer, because if I put this together you're going to see that the 3" and 600 thou isn't going to move our needle. We've also got selective thickness washers up here that we can use if we need them. So the idea here is we'll take our handle and we're going to take our dial indicator, and we have to put the two of these together. Take the protective cover off, and this dial indicator works just like any other dial indicator. As the plunger is depressed, the indicator is going to move around. In order to assemble this so that it's useful, first we're going to have to attach the dial indicator. So what we do is loosen off the thumb screw at the top, and it's hollow, and we're going to insert the dial indicator. Now we have to be careful here not to go too far, and I'll show you what I mean in just a second. What I want to do is very slowly drop the indicator in to the bore, and I'm looking for that little bit of needle movement there. See, at this point the needle stopped moving, I'm not down far enough. I want to just make contact. The reason for that is, if you see the button on the end, this is what's actually going to take our measurement. So if I squeeze this, you'll see the indicator move. And basically what's happening is, as this button is getting pushed in, a rod is acting on the base of the indicator on the top. If I install the indicator too far, it's going to start taking to the end, the indicator plunger to the end of its travel, and I won't get an accurate measurement. So I want to keep this as high as I possibly can while still affecting the measurement. Next thing I want to do is select the appropriate rod and spacers if need be. Now in this case I know that I want to use the 3" and 600 thou rod. This guy's got a bearing on the end of it so it slides smoothly. And the shoulder on the rod is where I want to put my selective thickness washers. So in this case, I'm going to add an extra 51 thousandths of an inch. And then another 20. I'm going to install that into my handle, put the cap on, and turn it till it's locked in place. I want to take a second and just talk about the dial indicator itself. Okay. If we look at the face here, we've got a couple of marks. First one here on this side indicates what each increment on the dial indicator means. In this case, we're talking half a thou, or 5/10,000ths of an inch. What that means is, for each of the small ticks, you see there's a small one, and then a longer one, and then a small one, and a longer one. Each of the small one is going to be half a thou, or 5/10 thou, and each of the long ones is going to be a full thou. If you come down to the bottom, you'll see that once we go 180 degrees on the dial, we have hit 25 1/1000ths of an inch in half thou increments. So this is going to be really important for us when we start to look at our taper and out of round, that we understand exactly how to read this gauge. The plunger here, you can see it moves on the top as well, so we've got to make sure that we don't put anything over top of this that is going to interfere with the movement of the plunger. Now with the dial bore gauge, this really isn't going to be an issue. And then we have another dial here, and this dial has a thumb wheel on it. And what that's for is if we turn it to unlock it, we can move our ring to zero the gauge, which is going to become important. Before we start actually taking our measurements, I think we better take a second and talk about where we're going to take our measurements. When it comes to any measurements inside the bore, we want to pay attention to ring travel. Now, this is a fairly new engine here, so we can't see a lot of wear or indications of ring travel except at the very bottom. So what I've done is I've come in and I've put a black line with a marker approximately where I would take my measurement at the top. Now what this indicates is the top of the ring travel. Of course, above this there's not going to be any contact with anything, so there really shouldn't be any wear. Down at the bottom, we're indicating the lower range of our ring travel. So really all of the wear in this block should come in between those two lines. What we would expect to see is our maximum point of wear very close to the top, and our minimum point of wear very close to the bottom. Reason for this, lubrication is going to be greatest at the bottom and least at the top, therefore we should have more wear at the top. And also, once we're at top dead center, on the compression stroke in the beginning of the power stroke, our pressures, or the pressures that the rings in the top of the piston are going to be subjected to, are going to be our highest. We know that on power, some of the combustion gases will be getting behind the rings and forcing them out against the block. So the highest pressure loading that the cylinder is going to see is going to happen at the top, where we also have our lowest point of lubrication. As far as relation to the crankshaft, we should see our maximum wear 90 degrees to the center line of the crankshaft. Again, this is because of our major and minor thrust sides, and we know that the wrist pin is going to allow the piston to pivot in line with the crankshaft, which means that any tipping and transfer of force as the piston crosses over top dead center is going to happen at 90 degrees to the crankshaft. So when we're looking for cylinder wear, we're going to measure at 90 degrees to the crankshaft center line. Out of round, of course, we're going to have to check both. And for taper, we're going to look 90 degrees to the crankshaft center line again. Once I've established where I want to make my measurements and I've got my bore gauge set up, I'm going to drop it down into the cylinder. And the first thing I want to do, I'm going to rock it all the way forward so that the needle doesn't move, and I'm going to rock it all the way back. And I want to make sure that the needle on that dial indicator doesn't go more than a full 360 degrees. When we actually do our measurements, I'll show you why we don't want that. But in this case, we're good. So I'm going to slide up to my top measurement, and I'm going to rock the gauge back and forth. Now you'll notice right there, the needle reverses direction. What's happening is I've hit my smallest measurement, or where I'm totally perpendicular, right where the needle stops there. So what I'm going to want to do is find that spot and zero my indicator. So I've zeroed my indicator, and you can tell now that when I go back and forth, the needle stops at that zero. So I'm going to use that when I actually do my bore measurement, but I'm also going to use this as an indication for taper. So this is my measurement at the top. To check for taper, all I have to do, slide down to the bottom and repeat the same thing. If the needle reverses directions on the same zero, I don't have any taper. What that indicates is we have the same size, top and bottom. If the needle reversed direction one full tick down, one of the larger ticks, I'd have a thou of taper. If it was a half, then it would be reversing direction at the smaller. But I don't need to do any actual measurements here to find this out. All I need to do is compare the top and the bottom. Similarly, without a round, if I come back to the top, make sure my zero is still good. All I need to do now is at the same point, turn 90 degrees and check it this way. And of course, you can't see it. I'll turn the indicator. Now this may skew my accuracy, unfortunately. And it definitely did. But all I'm doing is checking 90 degrees to my original measurement, and that's how I'm going to check for out around. So taper, top and bottom in the same plane. out around at the top, 90 degrees out. So I've turned my dial indicator 90 degrees so that the bore gauge will lay flat, and it'll make this next step a little bit easier. After I did that, I reset my zero at my point of maximum wear, top of the ring travel, 90 degrees to the crank center line. To find out what the actual bore measurement is here, I'm simply going to take an outside micrometer to the bore gauge, and I'm going to use the mic almost like a clamp to squeeze the bore gauge and turn the indicator back to the zero. This is why it's very important to make sure that when we're setting our bore gauge up, it doesn't go all the way around more than 360 degrees. If it does, we're going to have to keep track of how many turns, and it just makes this step more complicated. I wanted to zoom in on the gauge here, just so you can see exactly what I'm doing with the micrometer. I'm just slowly tightening it until the indicator on the bore gauge comes around to zero. At this point, I'm going to lock the micrometer, remove it, and read it to get my maximum bore diameter.